Hello, folks. So we are into the last week of actually substantive material. Very exciting. And this last lesson is on significance levels. So we're going to really talk through two different sets of things. One are about p-values, and then the second thing is about confidence intervals. And so when we talk about significance levels, and you should have now, in preparation for watching this lesson, read the Salkind Chapter 9 textbook to at least start getting the hang of some of these ideas. But if you've done the reading, then you'll see that this idea of significance level is used to express the risk we're willing to take with not being 100% confident that our analysis results are correct. So when we actually start doing inferential statistics in Soc 302 next semester, you'll see that there's always going to be something related to what's called a p-value. And we can set our p-value at a certain level of risk. You can think about what is the chance that we're willing to get the analysis wrong as what significance level means. So if we have a p-value that's set at 0.05, that means there's a 1 in 20 chance, or 5 out of 100, right? A 5% chance that our analysis is not correct, that any differences that we found were not due to the hypothesized reason. So think back to when we were doing the null and alternative hypotheses, and our alternative hypothesis was always that there was an actual difference in mean on the dependent variable for the two groups of the independent variable. Well, what if our analysis reveals that there is a difference in our sample? Is that difference big enough for us to be able to conclude or generalize that there's also a difference between means in the population? There's always going to be a chance that we're drawing a conclusion about the population that's incorrect. And our significance level starts to give us a sense of how often we're going to be incorrect. So is any difference in the dependent variables actually due to something, including chance, that isn't the independent variable? So the most popular p-value we'll look at is that's used as 0.05. We can also set to be a little more stringent a p-value of 0.1. In that circumstance, we would say we're okay with being wrong 1 out of 10 times. Or we can do a p-value of 0.01, in which we would be wrong 1 out of 100 times. And again, these are all probabilities, thinking about the area under the curve. And for our purposes now, all I want to do is to get you practice in looking at p-values and making the conclusion of what we should be doing based off of that p-value. So if you have a p-value that's less than 0.05, that's this first one on the left, the less than 0.05, when that happens, then we reject the null hypothesis and say that there is a difference between groups. And I know you've seen several other times through the semester so far, there are way too many nerdy stats professors making silly memes on Twitter that I follow shamelessly. And yet, here's a great one with Snoop, that if the P is low, then the HO, the null hypothesis, must go. So if that helps you, remember that when the p-value is less than 0.05, that means we reject the null hypothesis, and say if we're rejecting the null hypothesis, that means we believe that the alternative hypothesis has some truth to it and that there is a difference between groups. Alternatively, we can say the p-value, our analysis might reveal that the p-value is greater than 0.05. If that happens, then we are failing to reject the null hypothesis. Fail to reject essentially means we're accepting the null hypothesis, but there's a lengthy explanation in statistics world about why we can never actually accept the null hypothesis, but only fail to reject it. We fail in our sample to find enough evidence that there is a difference. So when we fail to reject the null hypothesis, we're saying there is not a difference between groups, right? That the alternative hypothesis that says there is a difference in means on the dependent variable between groups is not correct. So if the p-value, if that number as your probability value is greater than 0.05, our conclusion is to fail to reject the null hypothesis. Again, one other silly stats meme to help you remember that one. So the interpretation for this of what these are really saying is, let's say we had a research question that was, do males or females spend more time on social media, right? This is, as a refresher, this is a non-directional question. We're not guessing males or females spend more time. We just think there's a difference in the means. So our null hypothesis would be that the mean number of hours per week on social media for males is equal to the mean number of hours per week on social media for females. Our alternative, or our research hypothesis, would be that the mean number of hours per week on social media for males does not equal the mean number of hours per week on social media for females. Then when we go and do these analyses in Social 302, the computer program Excel will give you a p-value, right? That it'll give you this value that is the key to determining whether or not we find support for the null or not. And so if there's a p-value that is given of 0.15, we draw the conclusion that we fail to reject the null. And if we don't reject the null, that means there's not a difference between means, right? The null is that the two groups are equal. Or if you ended up with a p-value that's less than 0.05, something like 0.03, then we would reject the null and conclude that there is a difference between means, because if, oops, sorry, moved too fast. If the null is incorrect, if we get rid of the null, that means the alternative is the correct one, and that this is the one that there is a difference between means. So all of this is, in my experience, trust me, it matters to like have this practice of just seeing what is the p-value and practice knowing if it's less than 0.05, that means we fail to reject the null. If it's, if it's less than 0.05, we reject the null. If it's greater than 0.05, we fail to reject the null. Again, this is like, we're just laying the groundwork for doing the more complicated stuff in 302. If you have a comfort level with just doing this basic step, trust me, it's going to make it a lot easier when we're doing the complicated stuff in 302. Okay, so kind of another example of thinking about p-value is, if let's say we were comparing test scores for kids who went to preschool to test scores for kids who didn't go to preschool, and we think that the mean test scores are going to be higher for kids who went to preschool or not. So our null hypothesis is that the mean test scores are equal for those who went to preschool and those who did not. The alternative hypothesis is that mean test scores for the kids who went to preschool are greater than for those who did not go to preschool. And so if we were actually going to do this as a study, we would take a sample of the population of kids and see that test scores are perhaps higher for kids in our sample who went to preschool, and we tried to, set aside anything else that might influence test scores, right? So we're making sure we're drawing a sample of kids who went to preschool and who didn't go to preschool, and they're similar in every other way, right? They're the same percentage gender, the same percentage of different racial groups and socioeconomic status. They go to the same quality of school starting for K-12, and we want to see then, controlling for all this other stuff that's the same, is there a difference just for going to preschool or not? But we can never be absolutely sure that a true difference exists in the population, right? So let's say we do the study in that way and we take our sample of kids who went to preschool and a sample of kids who didn't. How do we know that it's not just due to chance that the kids in our sample of preschoolers have a higher mean test score just due to sampling error, right? Just due to dumb luck, just due to chance. It's the same idea of, you can flip a coin 10 times in a row and get 10 heads in a row. Does that mean that there's something wrong with that coin? No, that's just dumb chance that you got lucky and flipped it 10 times in a row. Can you roll 6 sixes in a row with a die? Yes. Does that mean there's something wrong with that die or that it's weighted? No, it's just chance. So there's always going to be factors that influence the outcome, that influence something like test scores that we can't control for. So significance level and the inferential statistics we learn in 302 help us to think about how big do the differences between scores, between means, need to be for us to reject the null hypothesis and say that there actually is a difference in means in the population. And so the significance level is really the degree of risk we're willing to take that we reject a null hypothesis when it's actually true, right? That we say there's a difference between groups when really there isn't. And so a significance level of p is less than 0.05 indicates that we're right in rejecting the null hypothesis, right? It's good, we're making the right decision, we're confident that we're coming to the right conclusion. A p-value that's equal to 0.05 or greater than 0.05 means we shouldn't reject the null hypothesis because any difference between groups is not big enough for us to be confident that it's not just due to chance, but that it's actually due to the independent variable, that it's actually due to preschools having an effect on test scores. And so that's really what significance level is getting us to think through. But this is tricky because there's always a balance of getting it wrong. So there's, even with a p-value, if we set our p-value, our rule of rejecting the null hypothesis as low as a p equals 0.01 or less, that means we're only making the wrong decision in 1 out of every 100 times. So that we're saying there's a difference between groups when really there isn't, then it's still possible that we're getting it wrong. The reverse is also true, that if we set the p-value too high, then we could be rejecting the null hypothesis when we shouldn't be. And so there's 2 types of error that help us describe the 2 ways that we can get it wrong. So what's called type 1 error is when we reject a null hypothesis when it's actually true. We reject a null when we should fail to reject it. In other words, we're saying there are differences between groups, between means, when really in the population there are no differences between means. If the significance level is 0.01, for example, this means there's a 1% chance of rejecting the null hypothesis when it's actually true. The reverse of that is type 2 error. So type 2 error is when we accept a null hypothesis when it's actually false. We fail to reject a null when really we should reject it. So we're saying there are no differences between groups when really there are differences between groups. The better way to address type 2 error, the way that type 2 error is addressed, is with a larger sample size. If we have a bigger sample, we're more likely to be able to detect a difference between groups in the population, between groups in our sample, that we would then be able to make conclusions about the population. So type 1 is we say there's differences between groups based off of our sample, but really there aren't differences. Type 2 is we say there are no differences between groups, but really there are differences. Sorry, my dog is scratching in the background if that's the noise you're hearing. Okay. 2 visual representations to help you conceptualize type 1 and type 2 error. So this one in the top here, type 1 error can be thought of as a false positive, right? So for example, a doctor telling a man, you're pregnant. This is saying a false positive because obviously he's not pregnant. Type 2 error is a doctor telling a clearly pregnant woman, you're not pregnant. Type 2 error is a false negative. There's also a way to think through with this other illustration about what's reality. Think about this as what is the decision we should be making related to the null hypothesis versus what you actually do. So if it is actually somebody's birthday and you say happy birthday, that's the right thing. But if it's not somebody's birthday and you say happy birthday, that's a false positive. That's a type 1 error. Alternatively, if it is somebody's birthday and you say nothing, that's a type 2 error, right? That we've gotten it wrong in two different ways. Let me give you an example, thinking with statistical values more clearly. So there's different types of error. If we were asking a question, a research question that was like, is there a difference in the number of hours studied for freshmen versus seniors? An example of how we might see type 1 error could be that if we find, so we take a sample of freshmen and we take a sample of seniors and we take the mean number of hours that freshmen study per night and the mean number of hours that seniors study per night. And perhaps in our sample, we find that freshmen study, or in a week, would probably make more sense, right? Nobody's studying 20 hours a day. In a week, freshmen study 20 hours per day or 20 hours per week, and seniors study on average 30 hours per week. So our sample shows here that there's some differences, right? We find in our sample that there are differences in the mean hours studied between the two groups. And because there's differences, then we are rejecting our null hypothesis, right? Something like this would give us a p-value that's less than 0.05. We would see something like a p equals 0.03. And we conclude then we should be rejecting our null hypothesis because there's a difference between groups. But really, we just happen to sample more seniors who are high achievers and study a lot, because in the population, there aren't actually differences between the groups, and we should have failed to reject the null if our study was done properly, or if we didn't by chance just happen to have more of the high studying seniors, because in the population, there's actually not a difference in the mean hours studied for freshmen and seniors. This would be type 1 error. So that if you reject the null based off of your sample and say that there are differences between groups, when really in the population there aren't differences between groups, that's type 1 error. So think about, write down in your notes, type 1 error is we say there's differences between groups or conclude there's differences between groups based off of our sample, but in the population, there aren't differences between groups. In contrast, we can make the mistake in the opposite way and say that there aren't differences between groups based off of our sample, but really in the population, there are differences. So let's say we sample in another study and find that the mean hours per week studied for freshmen is 20, and the mean for seniors is exactly identical at 20 as well. This would probably give us a p-value of like 0.4 or something, right? And so if with a p-value of 0.4, this is greater than 0.05, so we fail to reject the null and conclude that there are no differences between groups. But in reality, in the population, there are differences between groups, and we should have rejected the null. In reality, in the population, the mean hours of studied for freshmen is greater than what it is for seniors in the population. So perhaps in this circumstance, we only sampled like 3 freshmen and 3 seniors, and they all just happened to, because our sample size wasn't big enough to be representative of the population, we didn't detect in that small sample a difference between groups. So type 2 error is when we conclude based off of our sample that there's no differences between groups, but in reality, in the population, there is a difference between groups. That's type 2 error. Okay. All right. Second big chunk of today's lesson then. So that's kind of like the p-values and significance types of error part. Second chunk of today's lesson is the one that we do a little bit of math. And this is on confidence intervals. So confidence intervals are a way for us to estimate the percentage of all values in a given range. So this is the best estimate of the range of a population value or a population parameter given the sample value or sample statistic. So this looks and sounds more complicated than it is. In reality, the math for this is very straightforward and very simple. So where this comes from is we want to be able to say, if we know a mean, 95% of all values would be within what range? Remember, a z-score is the number of standard deviations away from the mean a given value is. So in some ways, doing confidence intervals is kind of like finding the reverse information of what we did with z-scores. With z-scores, I would give you what's a given value somewhere under the curve, and you would have to say what percentage of values are greater than or less than that value by using z-scores. Confidence intervals now says, given the mean and the standard deviation, what is this value here and this value here, so that we can say 95% of all values are within this range. And where this negative 1.96 and positive 1.96 comes from is, if the goal is to be able to say 95% of all values fall between blank and blank, we know a z-score of 1.96 is associated with 47.5% of all values between that z-score and the mean. If you don't believe me, go ahead and check your z-scores table, and you'll see that a z-score of 1.96 has 47.5% of all values. 47.5% of all values times 2 is 95. So confidence intervals are saying, if we know the mean and the standard deviation, how can we say we can be 95% confident, or 95% of all values fall between what value is here and what value is here? So again, this is kind of like the opposite of z-scores. In order to do this, you're using the formula that is the mean plus or minus 1.96 times the standard deviation. So a 95% probability of a raw score falling within plus or minus 1.96 standard deviations, or z-scores, of the mean. So let's say we have a sample of test scores with a mean of 80 and a standard deviation of 3. And to do this, our formula that we use is the mean plus or minus 1.96 times 3. So if we go ahead and do the math for this, we do 1.96 times 3 plus 80 gives us 85.88. And then if we also do 80 minus 1.96 times 3, that gives us 74.12. So we can say we're 95% confident that the population mean is between this value of 74.12 and this value of 85.88. So confidence intervals allow us to say, given a sample mean and a sample standard deviation, what's the range for the population of which we're 95% confident it's going to be between these two values. We can do the same thing with being more confident at 99%, right? So instead of now using a z-score of 1.96, if we're using a z-score of 2.56, a z-score of 2.56 is associated with 49.48% of all values between that z-score and the mean. So 49.48 times 2 is 99% of all values. So if we have a sample mean and a sample standard deviation, we can figure out we're 99% confident that the population mean is going to be between what value and what value. So the formula again for this one is we're just changing out the 1.96 to 2.56, and we do our mean plus or minus 2.56 times our standard deviation. So here, our mean of 80 plus 2.56 times 3 gives us a high end of 87.68. 80 minus 2.56 times 3 gives us a low end of 72.32. So this is essentially saying now we're 99% confident that the population mean is between these two values. Let's do some practice for these, and we'll see that the math is actually pretty straightforward. So let's say we have a sample distribution with a mean of 184 and a standard deviation of 43. How would we do a 95% confidence interval and a 99% confidence interval for that? So again, the formula is mean plus and minus. It's not because you're doing both, plus and minus. The 1.96 times the standard deviation gives us the 95% confidence interval. So 1.96 times 43 is 84.28. We're first doing it with the addition. So 184 plus 1.96 times 43 is 84.28. That gives us a high end of 268.28. Then we do the 184 minus the 1.96 times 43, the 84.28, to get a low end of 99.72. So now we can say in a distribution with a sample mean of 184 and a standard deviation of 43, we are 95% confident that the population mean is somewhere between 99.72 and 268.28. 95% of all values are between this range. Then to do the 99% confidence interval, we're doing the same thing, just subbing out a 2.56 instead of the 1.96. So first, 2.56 times 43 gives us this 110.08. Our mean, 184 plus 110.08 gives us the high end. 184 minus 110.08 gives us the low end. So we can say 99% of all values are between 73.92 and 294.08. Or another way to say it is that we're 99% confident that the population mean falls between this range. Another practice, for a distribution with a mean of 356 and a standard deviation of 48, create the 95 and the 99% confidence intervals. Same thing, it's our mean plus minus our 1.96 times our standard deviation gets us the 95% confidence interval. So 1.96 times 48 is 94.08. 356 plus 94.08 gives us 450.08. Then 356 minus 94.08 gives us the low end of 261.92. So we know there's 95% of all values fall between this range of 261 and 450, or we're 95% confident that the population mean is in this range. Same idea for the 99% interval, that we have now just the 2.56 instead of 1.96. So 2.56 times 48 is 122.88. 356 plus that gives us the high end. 356 minus the 122 gives us the low end. 99% of all values are between 233 and 478. Then our last practice for this one, I would encourage you, if you didn't do this for the first two, pause now, see if you can do this one on your own, and then I'll flash you the answers in just a second. All right, so hopefully this is going to match what you have on your own paper. Again, the formula always mean plus or minus 1.96 times the standard deviation for our 95% confidence interval. 1.96 times 2.59 gives us the 507.64. When you add that to the mean, that gives us the high end. When you subtract it from the mean, that gives us the low end. So here, note that when the standard deviation is relatively small compared to a really big mean, this means we have a relatively small range, right? That we can be, and sorry, I see there's a typo here that this should say 157,087, not 156, my apologies. It's correct here. But this is a relatively small range of $156,000 to $157,000 are between that range. Then the 99% confidence interval is a little larger, 2.56 times 259 gives us 663.04. Add that to the 156,000, that gives us 157,000 and change. Subtract it from the mean, that gives us the low end of 155 and change. So we're not 99% confident that the population mean falls between these two values. Okay, and that's it. Hope you're feeling good about the thinking about p-values, the types of error, as well as the confidence intervals. Go ahead and move on now to the classwork. Send me questions as they come up, and keep up the good work, guys. I'll talk to you soon.